our textbook. So in our textbook, it's in chapter 7, section 4. But of course, in our notes, we are labeling this as 7.3, part 4. Okay, so let's review. We already started talking about this a little bit in class, so I'm not really going to go over it too much, but the idea is that we have the distance formula, which we know from way back, and it's basically used to identify the distance from one point to the next. So what is the distance between 2 points on a graph? Now the distance formula is all about line segments, straight lines. So the idea is that if we increase the number of line segments from one point to the next, so if I increase the number of lines, all right, so if I have a line segment from this point to this point, and then another line segment from this point to this point, and so on. Right, these are not the best lines, but and I add up all of these different line segments, I can get a better approximation of the length of the whole entire curve rather than just from the beginning to the end. So where did that formula come from? So the formula is derived from the distance formula. So we already know the distance from one point to the next is x2 minus x1 squared plus y squared minus y1 squared. Now in calculus, we know that the change x2 minus x1 is representing the change in x, and so is y2 minus y1 representing the change in y. So we're going to rewrite it like we do in calculus as dx squared plus dy squared. Now that is pretty basic. So where we go from here, it takes a little bit more of a proof. Now, do you have to know how to solve this proof? Absolutely not. You just have to know what this formula, where it originated from and what it gave us. All right, the next step in deriving the formula for length of a curve over the interval comes by multiplying this distance formula by dx over dx. So by multiplying by dx over dx, remember we're not changing anything, okay? This dx over dx is technically still 1. But remember, this is a proof of how they got to the distance formula. So by multiplying by dx over dx, and next we wanted to move one of these dx's into the radical. Now, of course, we're going to move the bottom one because in order to integrate, remember we need a Leibniz notation, which is represented by a dx in the numerator. So we're going to move that bottom denominator into the radical. And of course, if we move that into the radical, it has to be rewritten as 1 over dx squared, because then once you square with the top and the bottom, and you can take it back up and end up with a dx on the bottom. Now, next up is to distribute that dx squared. Okay. And that way we end up with dx squared over dx squared plus dy squared over dx squared, and then times dx on the top. And then, of course, dx squared over dx squared ends up giving us a 1 plus dy squared over dx squared stays as dy over dx, or the integral, the derivative squared times dx. So right here, this formula gives the distance of one very small line segment on the curve. Okay, so it might give us this one very small line segment right here. And then, of course, in order to find all the sums of all the line segments, aka the length of the arc, what you would do is you would integrate it from one point, forgot the dx, integrate it from one point to the next, which brings us to the actual equation. So the arc length of a curve from A to B is found by, for a function f of x, the integral from A to B of the square root of 1 plus the derivative of that function squared times dx. So this formula gives us the distance of many really small line segments on the curve, adding them all up, and therefore finding the actual length of the curve. Similarly, for a smooth curve that is in terms of y, the arc length of g of x between c and d being y values, right? Because the dy represents the change in y, is still the same. It's 1 plus the derivative of the function in terms of y squared. All right, when finding the derivative of a function, you take the derivative with respect to the variable your function is in terms of. In other words, treat the variable that is solved for as y and the variable in the function as x. So we got our input and, of course, our output. Here are a few examples. So the derivative, if the function is f of x equals 3x squared, that's easy. You're taking the derivative of the function of x. Okay, so that's going to be 6x. Now, if you have a function in terms of y, it's going to be 8y cubed plus 3. So if you have the derivative in terms of t, you're going to derive that in terms of t. Okay. So here are some examples, and they're not that hard. I'm not going to plug anything into the calculator. You guys can, but the majority of these are in the calculators. So find the length of the curve, y equals x cubed over 6 plus 1 plus 2x over the interval from a to b 1/2 to 2. So remember, if the function is y equals x cubed over 6 plus 1 over 2x, we need, in order to figure out the length of the curve, so our formula is 1 plus the derivative, so y prime squared dx. So I need to figure out the derivative of this function. Okay? So remember derivative, the 3 comes down, so 3/6 becomes 1/2 x squared. And then if you move this guy up, this ends up being minus 1 over 2x squared. So here's our derivative. Now the rest is just easy. It's a plug and chug. So it's going to be 1 plus the derivative of the function, which is 1/2 x squared minus 1 over 2x squared, all of that squared dx. Now, we did forget that this is right here the distance of one small segment. We want the whole length, so we're going to integrate that from 1/2 to 2. So this problem right here, you could try to factor it out and find it, but honestly, the majority of the times, like I said, these problems are in the calculator. So on the quiz, most likely I'm just going to be asking you guys to set up the integral. If we have a calculator option, then you can plug that into the calculator and you will get 2.063. All right, find the length of the curve. Again, to find the length of the curve, the formula is going to be the integral from 0 to 1 of the square root of 1 plus y prime squared. It is in terms of x, so I'm taking that derivative in terms of x. So it's 0 to 1 of 1 plus, we got to get the y prime. So in this case, when the 3/2 comes down, that cancels out the 2/3, so that guy comes down, cancels out the 2/3, subtract 1, so you end up with x to the half, and then plus the derivative of 1 is 0. So it's just going to be x to the half squared dx. Plug that into the calculator, and you get 1.219. Okay, find the length of the curve of x equals e to the negative y from y equals 0 to y equals 2. So here we got to get x prime, and the derivative of e to the negative y is just e to the negative y times the derivative of the stuff, which is times negative 1. So the derivative is negative e to the negative y. And you see they already give you the bounds in terms of y, so makes it easy. It's going to be from 0 to 2 of the square root of 1 plus negative e to the negative y squared dy when you set it up. So remember, if I ask you to set up, you're going to have to get all of these parts correct. 2.21. All right, I'll leave you guys to figure this one out. The final answer in the calculator is going to be 3.142. Just to double check, if you have any questions, you can ask about it in class tomorrow. All right, which brings us to our last example. A manufacturer of corrugated panel roofing wants to produce C panels that are 28 inches wide and 2 inches thick by processing flat sheets of metal as shown in the figure below. The profile of the roofing takes the shape of the sine wave y equals sine of pi x over 7. Find the width of a flat sheet of metal, a flat metal sheet that is needed to make a 28-inch panel. Assume the process does not stretch the material. And of course, you're always going to round everything to 3 decimal places. All right. So to make 28 inches, the idea is how long does the flat sheet need to be? Which is what we've been doing, right? We want to measure the length completely of this arc. Now this 28 is basically the distance from this point to this point a straight distance. We want the length of the arc. So in this case, the length of the arc is actually representing the width of the flat sheet. Okay, if we stretched it out. So as soon as you understand that, then the rest is easy. It's going to be the integral from 0 to 28, because that's how long we want our panel, of the square root of 1 plus the derivative of this function squared, excuse me, times dx. So we got to figure out what y prime is, and of course y prime, or the derivative of sine of something, is going to be cosine of that something times the derivative of that stuff, which is pi over 7. So we're going to plug that in, cosine of pi x over 7 times pi over 7 squared. Put that into the calculator, and we end up with 29.361 inches wide. All right, that's it for arc length. It's not that hard. You have to know the formula. All right, good luck, guys.